Welcome, everyone. In this lesson, we're going to start talking about antidifferentiation. All right, so first, a little bit of an overview. What is this? And we really want to think of antidifferentiation is it kind of undoes differentiation. All right, so if we have a function, call it capital F of x, and we know, this is basically what we've been doing the whole entire course, is we know that there's a process to calculate its derivative, and we call that process differentiation. And we've learned a whole bunch of derivative rules that help us calculate f prime of x. And what we're going to learn is, well, we're used to going from one function and then figuring out its derivative. So we're kind of used to this one direction. But what we're going to start to see is if we have the derivative, how do we work backwards? How do we uncover that original function? And we call this process antidifferentiation. Or indefinite integration, kind of a synonym here. And what we're going to see is that the integration in general is not as clear-cut as differentiation. So kind of this working backwards is not going to be quite as easy as differentiation. But there's still going to be a whole bunch of rules that we can learn that help us with this anti-differentiation process. And we really want to think of these as they're kind of reverse processes of each other. They kind of undo each other. All right, so what do we mean? Let's look at the definition of antiderivative. All right, so let's read through this. A function capital F is said to be the antiderivative of a function little f if we differentiate the antiderivative and we get the function little f of x. So this is the definition. And what we're going to do is we're going to try a little example just to kind of think about what this definition means. So our function here, our example here, little f of x is going to be x squared. And what we're going to show is that there's actually a few antiderivatives of the function x squared. So we're going to show that 1/3 x cubed is an antiderivative, and we're going to show that 1/3 x cubed plus 1 is an antiderivative. All right, so what we're going to do, the way something is an antiderivative is we're going to differentiate it, and we should get out our function. All right, so let's check this. We're going to check capital F1. So that means we want to calculate the derivative, capital F1 prime. And let's differentiate our function 1/3 x cubed. So when we differentiate, the 1/3 stays in front, and then we differentiate the x cubed using power rules, so we get 3x squared. If we clean that up, we end up with x squared, which is what little f of x is. All right. So, check. The fact that capital F1 prime is equal to little f of x means that it's an antiderivative. And the way to kind of graphically think of this again is we have capital F, the function capital F1, and we saw that when we differentiate, we get little f of x, x squared in this case. And we have our 1/3 x cubed. And so if we were to start with x squared, the antiderivative of that is going to be 1/3 x cubed. or the indefinite integral, we're going to call it. Well, that's just one example. It turns out that x squared is actually going to have a whole bunch of antiderivatives, so we could play the same game for f2 of x, this function 1/3 x cubed plus 1. We can differentiate, so let's calculate f2 prime. Let's differentiate this entire function, and what we end up with is, well, same derivative. Derivative of, derivative, the 1/3 sticks in front. We differentiate the x cubed, we get 3x squared, and then the derivative of that plus 1 is just 0. And if we clean that up, the 3 and the 1/3 cancel out, and plus 0 we don't normally include, so we end up with x squared. And this shows that capital F2 prime is equal to little f of x. So we end up with the same kind of scenario here, that we had f2 of x, which was 1/3 x cubed, and we have our function little f of x equal to x squared, and using our regular derivative rules, we saw that f2 was, the derivative of f2 was actually just our x squared function, but we could think of this in reverse. So we could think of the antiderivative of x squared as being this 1/3 x cubed plus 1. All right, so what we're seeing here is that x squared, the function x squared, has at least 2 antiderivatives. Well, it turns out there's not too much special about this plus 1. So if this was any constant, plus 5 or plus 10 or plus 100 or plus 1 million, that would still give us an antiderivative. And so usually a function has many, many different types of antiderivatives, but they're all kind of similar to each other. Really, the main part here is this variable part. That's what really kind of makes this antiderivative stand out. The constant that gets added on at the end, yeah, it changes things, but it doesn't change things that much. And so we have a property that if we have 2 antiderivatives for the same function, well, we'll call them f1 and f2. Well, it turns out they're almost equal to each other. They're basically equal to each other. They only differ by a constant. So they're pretty close. Not quite the same, but they differ by a constant. And so what we're going to do is we're going to generalize things. So rather than getting hung up on kind of particular antiderivatives normally, what we do is we're going to be using capital F of x plus constant c to represent all antiderivatives. Of some function little f of x. So basically what we're going to be doing is focusing in on the variable part, and then we're going to throw a general plus c on the end, saying we found the interesting variable part, and then there's some ambiguity in terms of the constant that's getting added on. All right. So what do 2 antiderivatives look like? Well, we kind of want to think of them, we want to compare them to really parallel lines in some way. So in this first graph over here, this is the graph of 2 antiderivatives of x squared. Actually, the 2 antiderivatives we were just looking at. So we had 1/3 x cubed plus 1, and then we had 1/3 x cubed. All right, so just a few properties of these. The fact that we've added on this plus 1 means that it's basically just a vertical translation. So you pick any 2 common points on this graph, and they're going to be plus 1 units apart. So for instance, if I pick these 2 points, we have 1 unit of separation because of that plus 1, that constant that's being added on. If I pick two other corresponding points, maybe here and here, again, there's 1 unit of separation. So comparing these two things, they're really vertical translations. That's all that constant c does, is it just slides the graph up or down. So the variable part is what is really what's interesting, and then that plus c, that constant, just kind of moves things up or down depending. All right, so two antiderivatives, they're just vertical translations of each other. The other thing that the antiderivatives share is that they each have the same slope at corresponding x values. So if I were to kind of pick the corresponding point on each antiderivative, and if I were to look at the slope at each of those points, they're going to be, the tangent lines are going to be parallel. The two tangent lines are going to have the same slope at those corresponding points. Or if I were to pick these 2 points, draw in the tangent lines are going to be parallel. They're going to have the same slope. So our two antiderivatives, or any two antiderivatives, they're going to kind of be like parallel curves. They're going to be vertical translations of each other, and they're going to have the same slope at corresponding x values. And that's really what, if we kind of look over to the graph over here, that's really the way two parallel lines work. So two parallel lines, they have the same slope, and they're vertical translations of each other. So if I were to kind of pick two corresponding points, and all the points are going to have the same kind of separation in between them. Okay, so that's the way to kind of picture antiderivatives, is all the different antiderivatives we can find for a function, they're all kind of like parallel curves. All right, so let's start getting into our notation a little bit. So generally, the notation we're going to be using when we talk about antiderivatives, we're going to call these things indefinite integrals. All right, so let's suppose that little f of x is a function whose antiderivatives are capital F of x plus c. The way we're going to write this is we're going to have this kind of elongated s. So this is like a really fancy s that we put in front. And we kind of stretch it out. And we call that the integral sign. And then on the other side, so that's the first part of our notation here. Then on the other side, kind of like bookends here, this dx, we're going to call this the differential. And it basically tells us what variable we're doing the antiderivative for. So in this case, dx tells us our variable here is x. So that's kind of specifies the variable. And then the function that goes in the middle, little f of x, that's the function that we're trying to integrate. And we call that the integrand. Sometimes. If we feel like being fancy, we call that the integrand. That's the function we're trying to integrate. All right, so this notation here, and then on the other side of this equal sign, this is the actual antiderivative, and then we throw our plus c on at the end just to denote that we have our main variable part, and then we might be off by a constant, so we make the adjustment. And the variable notation here, we would use something, there would be similar notation if we were using something like, say, variable t. So if we were integrating with respect to variable t, well, how the notation would look, we'd have our integral sign in front, our function would be f of t, and then our differential would be dt, telling us that we're integrating with respect to t. And so you kind of want to think of this integral sign with the dx at the end, this is really directions telling us to integrate everything inside here with respect to x. So that's kind of like the notation that we've seen before for derivatives. So sometimes we use this d dx notation for derivatives, and what this tells us is it tells us to differentiate everything inside here with respect to x. So we have our antiderivative notation and we have our differentiation notation. All right, so let's get into a few of the basic rules. And kind of the main one that we're going to see is right here, power rule. So basically, all the derivative rules that we've learned, there's going to be kind of an analogous anti-differentiation rule or integration rule that we're going to see. And so the main derivative rule, going all the way back to just about the beginning of the course that we've been using all along, is the power rule. And so what this one tells us to do, or tells us how to do, is it tells us how to integrate a power function. So that's what we have here, is a power function. And so essentially, this is the opposite of our derivative power rule. All right, so let's see how this thing works. And once you get the hang of this, you're not going to really memorize what this rule says. You're going to think of it more like a process. So the first step when we do power rule for indefinite integration, or for integration, we're going to, let's write down our function, x raised to the power r. And the first step is we're going to keep our variable the same. So we started with an x, we're going to keep it x. So we're just going to keep our variable the same here. All right. So then the next step, step 2, is we're going to take our old exponent, which was 4, or not 4, which was r. That's an r there. We're going to take our old exponent, which is r, and we're going to add 1 to it. So the second step is add 1 to our exponent. All right, so then once we have this new exponent, the last thing we're going to do for our power rule is we're going to take that new exponent, flip it, and put it in front. And that's kind of step 3. We're going to put the reciprocal of the new exponent in front. And that's kind of the process we want to think of here. So the first thing is we're going to keep our variable the same. Then we're going to add 1 to the exponent. And then we're going to take that new exponent and flip it, put it in front of the variable. And once we start doing these, normally with derivatives, what we do, if we're going to do our derivative power rule, we subtract 1 from the exponent. Well, with this integration power rule, we're adding 1. So we're trying to undo the derivative. So if we subtracted 1 for the derivative, to undo that, well, we got to add 1 back. And one little note here. This power rule only works for r not equal to -1. So this exponent can't be -1. So what we're going to see is that if we're integrating x raised to the -1, well, we're going to write that as integral of 1 over x, and that is a different rule. That's our log rule down here. And we'll talk more about that one a little later. So all we have to know is that for when the exponent's -1, we can't use power rule. All right, so let's try a little example. So we have the formula for power rule, and let's we're not going to go through all these. We'll save some of this for class, but let's get a little taste of the power rule here. All right, so let's look at this first one. Example 1, part 1. We're going to do the integral of square root x with respect to x. And when we do this, kind of the same strategies that we use for differentiation, we're going to kind of use them again for integration. So normally when we have a power, or when we have a root function, we want to get rid of the root signs. We want to rewrite it as a power function. Same deal here. So we're going to rewrite the nth root of something as raised to the power 1 over n, just like we would do for if we had to do the derivative. So let's write this as x raised to the 1/2. So square root x we can just rewrite. Now this x raised to the 1/2 is a power function. So now we're going to do our power rule. So how does our power rule work? First step, we keep the variable the same. So we're going to keep it as x. Then we're going to add 1 to this old exponent. So our old exponent was 1/2, and we're going to add 1 to that. And it doesn't hurt to show this step, but once you get the hang of it, you're probably not going to show 1/2 plus 1. And actually, let's kind of work this out. And especially with fractions, it doesn't hurt to kind of do this off to the side. So we want to add 1/2 with 1 here. And if you have trouble, kind of work this out separately. That plus 1, we could get a common denominator, so 2 over 2, and we end up with 3 over 2. All right, so let's actually fill that in. So our new exponent is going to be 3 over 2. All right, so what does power rule say? First thing, we keep our variable the same. Then we add 1 to the exponent. We did that, we got 3/2. Then we're going to take our new exponent and we're going to flip it. So we're going to put the reciprocal of it in front. So our new exponent is 3 over 2. We're going to put 2 over 3 right in front. And then as soon as we're done with the power rule here, that basically takes care of this x to the 1/2. We're just about done. And all that's left is we're going to throw on the plus c at the end. And that's power rule. All right, let's try one more. We'll save the exponential for later, but let's try 1 over x squared. It's going to be another power rule one. And just like root functions, there's something similar we would do for fractions if we were going to try and differentiate. And our main strategy here is to rewrite fractions using negative exponents. It's kind of one of our main strategies. All right, so let's do it. Let's rewrite this as x raised to the -2. All right, so now this is a power function. Power rule is going to work. So the first step is we keep our variable the same. Then we're going to add 1 to this old exponent. So we're going to have -2 plus 1. So that's going to give us -1. Again, the way we're getting this new exponent is we're taking our old one and then adding 1 to it. And then we take our new exponent, flip it, and put it in front. So we're going to end up with 1 over -1. And as soon as we're done with our with our power rule there, we throw on the plus c at the end. And, we can clean this up. 1 over -1 is just going to be -1. And it doesn't hurt. Once we're done getting the antiderivative, rewrite it back as a fraction. So we could rewrite this as -1 over x plus c. Again, not absolutely necessary, but also fine just to leave it right there. All right, so just a little bit of practice with power rule. And what we're going to kind of see in class is that there's a whole bunch of other rules that we're going to be able to learn to help us differentiate, well, exponentials, and then get the log function here as well. And then on top of these, there's rules that tell us how to put all of this together and be able to differentiate more complicated functions. So we'll see you then. Bye-bye.